Welcome everybody to Medical Myths. Although today's a little bit different because it's more of a class than a usual debunkathon this morning. But before we get into this, I do want to share out some love from the side chat. We got Anjur saying, "Glad to see you back, Scientist Mel. Hope you're doing well." And yes, Scientist Mel has been in this community long before I ever joined this. So it's good to see some love in the side chat. But you all know who I am. Uh, Scientist Mel, would you like to share kind of who you are and what you do?
Sure. So I'm Scientist Mel. I started science communication probably in 2015, and I just, I felt like a pressing need to talk about what goes on in the world for people to understand how things work. And then when the 2016 election happened, I was like, boy, I really need to talk about some things because my goodness, it was just a holy mess. But there's a wide amount of misinformation, and people just fundamentally just do not understand how science works. And I try to develop a open and you know atmosphere to where people could come and learn things without being judged for not knowing how things work. I think that's really, really important. So, yeah, so I'm by trade, I'm actually a chemistry professor where I teach. It's a high needs community. There's a lot of um, marginalized communities in the area, and their backgrounds in science are really kind of just woo, and it's a diverse crowd. So I really enjoy what I do, but it takes a lot of my time. I've been able to build some really cool programs there. I built their first peer mentor program. I have an actual club for undergraduate research, and we're looking at developing credit for actual undergraduate credit for research, even though it's a small little 2-year college. But we meet the students where they're at. And currently, some happy news. I had one student that got an internship to Blue Marble Space, which is an affiliate of NASA, which is really awesome. So she worked hard and she got there.
Super cool.
Yeah, I have another student who is getting into medical research who is looking at, he's just applied for an internship over the summer at Harvard. So
Wow,
I think he's shortlisted. So fingers crossed.
that's
So
awesome.
it's a lot. So while I've been kind of absent here a bit, the good news is I'm still doing a lot of work with that. So I'm happy to be back. So thanks for having me, Ben.
Yeah, and of course, I brought you back for a very specific reason. And for people who aren't quite familiar with what we've been talking about the past couple months, we've been getting into a lot of debunking anti-vax pseudoscience, and also getting into the wellness industry and debunking a lot of those claims. But um, I realize there's kind of a disconnect because, of course, you and I have a foundation in science and in chemistry. So it's easy to say, oh, I know the difference between ethyl mercury, methyl mercury, elemental mercury. So it's easy for us to debunk those claims out in the open. But a lot of people don't really know beyond, like, where do we go from that argument? So I thought
Yeah.
we'd bring on Scientist Mel as a teacher, as a, like, this is what she does, is communicate this to newer scientists or people who aren't planning on being scientists.
Yeah.
Um, and going from that, like that newbie phase into how can we be scientifically literate and like learn how to think
Right.
through chemistry. So
Right.
so Mel's going to do a lot of the talking today. We'll be taking questions in the side chat. So if you
Yes.
all either you put question, or I mean, even if you phrase it like a question, I'll be saving those up. But today's a lot of basics. Don't be scared away if you've never taken chemistry before, if you've never done science before in an academic setting. That is totally okay. This is
Okay.
for brand new people, so do not be alarmed. I do have one question for you before we get started, and I did prime you for this before the show. Um, But do you need to be good at math to understand organic chemistry?
No, no, you really don't. It's all conceptual. And I find a lot of my students who come in fresh from school, they're like, I want to do all the math things. So mathy math people actually struggle often with chemistry because they don't understand that the math is secondary. You have to apply the math to the concepts. Now, organic chemistry, there's really no math in it at all other than can you count to 4? Because that's how many bonds carbon makes. So it's like if you can count to 4, you're going to be okay with the maths.
If you can count to 4, you belong here in this side chat. So,
Yes.
so stick around. Don't be scared of it. With that being said, I guess I'll ask you the question: what
Sure.
is organic chemistry for people who may have heard the term, that may know, oh, that's the weed out class?
Well,
What exactly is it?
Organic chemistry essentially is the study of carbon in all of the way that it can bond through the lens of looking at it in living systems. Now, if we had living systems off world or something and they were carbon based, it would still be called organic chemistry. Um, but we look at it primarily through the lens of living systems because that's where we see a lot of the carbon chemistry anyway. So,
Awesome.
yeah.
Well, I'll let you kind of take it away, and I'll jump in with kind of questions or comments as they
Okay.
come. Or if you want me to jump in for something, let me know.
Okay, that's cool. So, in order to really understand a bit of how um, organic chemistry works, is everything that you're taught in general chemistry, you're taught like the periodic table and the elements. These are metals, these are non-metals. Most of the periodic table is metals. So if you can remember that, you're doing great. They all give off electrons and the non-metals take all the electrons. So when you're looking at a chemical reaction, what you're really doing is looking at where the electrons are going. They started here, now they're ending up here. The electrons are where all the action takes place. So in carbon, carbon's got 4 electrons in its outside shell, but it's trying really hard to make 8 bonds. So ionic compounds, we've got a transference of electrons. One, like a metal, is giving away its electrons, and a non-metal is catching them. But in a covalent bond, like what carbon does, it shares those electrons and it forms a stronger bond with whatever atom it's sharing those electrons with. Now, here's the important thing to remember. Wherever the electrons are is where the reaction is going to happen. If you can keep that in your brain, that's where a lot of this stuff is. So when you were talking about methyl mercury or ethyl mercury or all of these other things, people are like, this vaccine has mercury in it, or thimerosal. They don't really use that anymore because people panicked because they don't understand that once you bond something to something else, it doesn't behave that way anymore. It's a new thing. So have y'all heard of chlorine gas? That's a war crime. You know, you dump chlorine gas on a population, you're going to end up at The Hague, right? Have you ever seen sodium metal in water and what it does? I set curtains on fire in a first grader's like classroom, showing them how sodium enters into water and it breaks apart those water molecules. I mean, you're looking at a chemical fire. Now, fortunately, nobody was hurt and all, but I tell you, those kids will remember that till the day they die. We set curtains on fire. But sodium by itself, if you were to chew sodium metal, it'd blow your face off, right? It probably would, because you got water in your mouth. But, or if you were to breathe in chlorine gas, you're going to die a horrible death. But just from sodium getting rid of that electron, it causes an explosion of water. But if chlorine is catching it, now together, there's something that we put on our potatoes, you know, our French fries. It's salt. So atoms in their elemental form are going to behave very differently than if they're bonded to something, whether it's ionic or covalent. So the methyl ethyl mercury crowd, they're not understanding that those electrons that would be involved in those reactions in the elemental version are not there anymore. They've been given to non-metals. So it's going to behave differently. And people don't understand that. And that's where a lot of that hang up is. So any questions or anything, Ben?
Yeah, I mean, just a point, like going from the uh, kind of the anti-vax arguments, just adding in another argument that we hear a lot is related to food science, because you
Okay.
mentioned salt, right? So
Yeah.
the myth that there's that regular table salt is okay, but MSG or monosodium glutamate is somehow bad for you. What would you say, based on your knowledge, is a good way to refute that particular argument?
So the whole idea with the monosodium glutamate actually comes from a very racist perspective, to where it's the history of that is pretty interesting. People were saying that it's bad for used to. I don't know if you go back to the 80s, they said that any salt was bad for you. They're like, we find that an increase in salt causes an increase in high blood pressure. Well, the media went wild with that. And like, well, we got to take salt off at every table, only use this alternative salt thing. And, then monosodium glutamate, you can find in alternative salts. If you don't want to eat salts, you can have monosodium glutamate. And then that may not necessarily raise your blood pressure. But the fact of the matter is, we have all kinds of different atoms in our body that, if they were in a different form, would kill us. Did you know that Dr. Ben might know this, potassium chloride?
Yep.
Very bad for you, often used to euthanize animals who are very, very sick. You have potassium and chlorine in your body right now. But, I would go back to the whole, okay, this is where you've been kind of misled. You have all of these other things in your body and you're walking around just fine. Potassium chloride would kill you if it was injected into you straight, a certain amount all at once. But come on, I would go that route and say, you have things, if they happen to come together and form this all universally spread out over your body, came together in one big glump, yeah, you might die. But it's not like, oh, it's so hard to talk sometimes with people who don't quite understand that. But if you point out potassium chloride could kill you, but it's in your body right now, both of those atoms are freely floating. One of them is part of your nervous system. So,
And this is why too, like, we need to kind of move away a little bit from the identity of the compound arguments. Like, yes, the identity of the compound does matter, but
yes,
there's a lot of other variables that matter more so than the identity. For example, like, that's
yes,
why we're talking about structures today and mechanisms.
yes,
And like, if you think about the whole salt discussion, right, the reason why we care so much about sodium and potassium and all that is largely based on the charges that they carry, more so than the identity of the
right,
molecule. Like, because you have transporters that move positive atoms and kind of exchange out negative ones. And so a
right,
lot of that give and take is really what's driving the blood pressure mechanism. So like, think less about uh this compound is toxic, but think about in what dosage over what period of time. And if you
right,
have some kind of propaganda or some kind of advertisement saying that something is universally bad, and they're not giving those answers of how much over what period of time,
right.
in what context, then you probably don't need to believe them, right?
I mean, everything's edible at least once, so, but dosage matters. I like to tell my students, straight up pure water is very bad for you. If you
Hmm.
drink straight up pure water with no salt in it or no minerals or no electrolytes, you got osmosis going on your tongue cells. Then they're going to what? They're going to have all this water rush into your tongue cells, and you might experience a little bit of pain, and you'll just get thirstier because your cells are going to start exploding. So I would have students in my class go, "Pure water is bad for me." I'm like, yes. Too much pure water is a bad thing.
Yeah. A question from the side chat: is ammonium chloride safe to eat? It's an ingredient in salted licorice. Hunter has wanted to try it, but doesn't know what aluminum chloride is.
So aluminum chloride. Oh, it's ammonium chloride.
Oh, ammonium chloride.
Yeah.
Sorry, I cannot read today.
That's okay. So if you look up ammonium chloride, ammonium itself tends, if it was ammonia as the base that you would use to clean, I wouldn't really use it in that context. But it's a salt of hydrochloric acid. So if you understand a little bit about acid-base chemistry, if I have an ammonia and I have a hydrochloric acid, they're neutralizing one another. So the ammonium chloride will take on, it'll either take on the hydrogen to be, so ammonia will become ammonium ion by taking on that hydrogen. And then it now becomes what we call a conjugate acid. But if it's already attached to the chlorine, it's a non-issue. There are some people, I think it's actually in cough syrup as an expectorant. So as an expectorant in cough syrup and treating metabolic alkalosis, I wouldn't just go out to the store and buy me some and toss it back, because again, dosage matters. But it's used in different things. Yes, you can safely eat it. But it's, if you take in too much, then yeah, it's going to cause you a problem.
Yeah, and physiologically speaking, with any kind of ammonium versus ammonia, the ionized form changes its permeability across membranes. And so that's a big thing, especially in nephrology, with how does your body process nitrogen. That's a big thing that maybe is beyond the scope of today's talk, but maybe we can cover. Maybe we need to do a follow-up on acid-base stuff at some point.
Acid-base chemistry is pretty much how your body runs, if we're going to be honest, transferring hydrogens from one thing to another. All right. So let's talk about how is it in another lens, looking through another lens. We've looked at, okay, when something bonds to something else, it behaves differently, right? Here, let's talk about the concept of functional groups. So functional groups in organic chemistry are groups of atoms that come together onto a carbon molecule. And that's where all the action happens. I don't know if y'all ever watched MTV Cribs, and they'd have a celebrity would show you their house and their car, and they always go to the bedroom and they go, "This is where the magic happens," every single time. Well, if this was MTV Cribs, the functional groups would be, "This is where the magic happens. This is where the action is." So functional groups, we've got, oh geez, I guess I can, if you could share my screen, if I can. Yep. Okay. Let me pull up. So if you're interested in doing a deep dive on organic chemistry, let me see. This is going to be overwhelming at first, so I apologize.
Oh no, we lost Mel. Hopefully she'll be coming back in a second. Soon to be walking around snuggling with a box of salt and hissing at cardiologist. Yeah, I believe that's a reference to Dr. Glockenflecken. And I love his stuff. It's super funny. Hopefully Mel can get back into the stream. Welcome back.
Sorry about that. I hit the wrong button. So
no, you're good.
I'm out of practice. So if I share the screen, okay, here we go. Alrighty. Let me pick which tab I want to share real quick. Here we go. I think, here we go. Okay. Now this is a PDF file, so I'm sorry in advance, but this is a couple parts. I'm going to zoom in on a couple parts.
Right, there we go. Okay.
So I'm just going to zoom in on a couple of these so they don't look like, oh my God. So what is a functional group? Well, it's where all the magic happens. We've got got single bonded carbon. We got double bonded carbon. We even have triple bonded carbon. And there's all kinds of different shapes that this can make. That's why carbon's pretty awesome. And you notice sometimes when those double bonds are kind of spaced out like that, that has completely different properties as if it was just all single bonds. So let's look over here at some of these functional groups. Now you notice this says alcohol. We probably had quite a bit of that over the holiday. If you have a challenging family and you're like, I need something to get me through. Well, alcohol is anything with an OH group. And you notice there's this little letter R. That just means the rest of the molecule, right? Whatever this is, this could be like 47 carbons. It could be 1. It could be 3. But it doesn't matter because this is where the magic happens. So we've got our oxygen, we got our hydrogen. Here's another one where we've got an oxygen and it's got the rest of the molecule on either side. Here we've got our halogens, fluorine, chlorine, bromine, iodine, and then the rest of the molecule. So when we change these functional groups, we change out essentially how these molecules are going to react. Look at oxygen. Oxygen paired with a hydrogen is going to behave differently than if it has 2 carbons on the other side. Here, this what we call an aldehyde. We've got a double bonded oxygen, but there's a hydrogen over here, and then the rest of the molecule. We have all of these different ways that we can put oxygen and nitrogen and chlorine and put these all in all kinds of different ways to where we can get a molecule to behave differently. So a functional group is where all the electrons end up, right? This is where the electrons go. This is where the reaction happens. And it's super important because whatever type of functional group you have, you can predict what's going to happen when it interacts something else. And that's essentially a lot of what organic chemistry is. So here we've got fluorine, chlorine, bromine, and iodine. They behave similarly because they're all in the same family of elements. But as I mentioned, oxygen with this hydrogen versus oxygen attached to 2 other different things, they're going to behave completely differently. And it largely has to do with where the electrons are and how tightly bonded that oxygen is. So when you're dealing with anti-vaxxers and they're like, well, this has this in it and this has that in it, you know what? Send them to masteringorganicchemistry.com and say, y'all need to read a little bit because it is largely dependent on what that atom is attached to. This is just the first page. Here's more somewhere. Now, I'm a good professor. I don't make my students memorize all of the functional groups, but I make them learn the important ones: alcohols, ketones, aldehydes lead to carboxylic acids. I mean, just how we do with our formation of proteins. Our amino acids, well, guess where we got the term amino? Amine, because it's got a nitrogen in it. Carboxylic acid, that's the acid part of our amino acids. So I think maybe that's over here. And all the different ways we can bond with that. We've got enols. Look, there's an alcohol, but this time there's a double bond nearby. So the point I'm trying to make here is when dealing with people that are like, well, it's got this element in it, the fluoride people are on my last nerve. They really are. We have fluoride in our water. Yes, Yes, we do. You also have it in your body already. It's like, oh no, let me detoxify myself of fluorine. I'm like, well, you're probably going to die then. So like, you got to have a lot of
Yeah.
these things, but they don't understand that. So here's something for you. So essentially, why is it that these atoms behave differently when they're attached to other things? I mentioned where the electron's going, right? So if you look at an O2 molecule, oxygen, it bonds to itself with a double bond. The electrons are evenly shared between those two oxygens. One oxygen doesn't have them any more than the other oxygen. But you look at something like water, H2O, you have an oxygen and two hydrogens. Well, those hydrogens, they don't care about the electrons near as much as the oxygen does. Now, this always drove me nuts when my organic professor would say, well, carbon doesn't like to do that. I'm like, carbon is a freaking atom. It doesn't have feelings. Can you get to the nitty gritty of it? This makes no sense.
But also, isn't there that common like joke within like among chemistry students that carbon's a whore?
Oh,
Like,
yes.
isn't
The
that a
term
thing?
is promiscuous.
Yeah.
They call carbon promiscuous. That's an actual scientific term that they call carbon. You know, so if you ever want to watch something fun, you can look up the Elemental Party. It's from the Marie Curie Institute, and they have different people act like different elements at a party. So the noble gases are all in the corner on their phones, not talking to anybody because they don't react. Then you find potassium encounters water and then they fight because potassium is trying to get rid of its electrons. Um, and the thing that made me kind of nuts a bit about the organic professor going, well, carbon just doesn't like that. Well, it has to do with what we call energetically favorable instability. So what does energetically favorable look like? Oh, is that high energy? No, 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 no. That's not what the energetically favorable is. And that's a common misconception. Energetically favorable is probably what you're doing right now on a Saturday. You're in your jammies, you got your snacks around you, you're chilling out, you're watching a little TV, you got your drink nearby, so you don't have to get up and go get it. That's energetically favorable, not, whoa, we're at a club. You know what I mean? It's the opposite of that. So, an energetically favorable situation with an atom or a molecule is whatever form it can take with the lowest amount of energy possible. So, if you've got what I would consider sodium metal or potassium metal, it's super spazzy in its elemental form because the first thing it wants to do is get rid of those electrons. That's its stress, right? So what's stress for one element is joy for another. Chlorine is like, give me that. Chlorine is like one electron away from a full set, right? Maybe chlorine is an avid collector of something and it needs just one more comet for the full set of 8, and it's going to destroy things until it gets it. So it's important to note that these elements, when they get their energetically favorable form and in their stable form, usually it's just nothing's happening. So when they're bonded, when they're covalently bonded, it's kind of similar. So looking at like our alcohol here, I'm going to zoom in a little bit more on this. Looking at this alcohol here. All right. So you see this is the little negatives. It's got like a little Greek letter. I don't know what the Greek letter means because I just don't save space in my brain for that, but it's partial. It means partial. This is partial negative and this is partial positive, which means within this covalent bond, all of these electrons are moving more towards this oxygen because oxygen is the collector and hydrogen's like, oh, okay, you want this more than I do. So I'm going to let you have it a little bit more. So since oxygen has more of that negative charge and hydrogen has more of that positive charge, hydrogen's very stable in its positively charged form. So that hydrogen just can pop right off and leave and maybe go join up with another molecule. And this oxygen will be just fine sitting here in a full negative form. But if oxygen was bonded to another oxygen, there is no, you know, division of electrons. They are equally shared. So you can't bust up. I mean, you can bust up an oxygen molecule, but it's going to take a bit of energy and it's probably not worth it. If you had a hydrogen attached to that hydrogen will leave and it's just fine. Now you can pair up this oxygen with something else and maybe end up with another carbon, you know? So we can turn an alcohol into an ether just by convincing that hydrogen to leave in the presence of a strong base. And then in comes another carbon chain because, you know, carbon will hook up with just about anything because it's promiscuous. Now here, there's a slight positive side over here and a slight positive side over here because guess what? Carbon has about the same desire to hold on to electrons as hydrogen does. So oxygen can still hold on to all of those electrons there. So notice I'm constantly saying electrons because that's what chemistry is. It comes down to where the electron's going. So the functional group is going to determine how these particular molecules behave and in the presence of what. So that's what makes organic chemistry a bit of a puzzle. It's more of a puzzle of this is what I start with. What do I think is it going to end up with? And then you really start to do a deep dive and you go, okay, who's got the electrons? Who is missing the electrons? Can something come in and provide electrons for the thing that's missing electrons? So it's like a whole story. So if you like the idea of personifying atoms and say carbon, you know, is a jilted lover, you know, maybe in the case of like here, in this case, our halogens. Our halogens are what we call the most electronegative atoms, usually on the periodic table, the highest being fluorine. Fluorine doesn't quite act the same as chlorine, but we'll just say it's a spectrum. It's varying degrees. So here, chlorine, remember I said Cl2 is a war crime. It's a gas form. You breathe it in, it's going to tear up your lung cells and bust up all of those different molecules so it can get an electron. That's why it's so dangerous. So we look at chlorine and carbon here. Chlorine will very happily leave this carbon alone and take everything in this bond. It'll take everything. And then carbon is going to be a jilted lover. But if you got like an oxygen coming along and it's got extra electrons, it'll be like, I can provide what you need. You know, then all of a sudden, now carbon is bonding with oxygen, even though chlorine took everything. That's what we call a substitution reaction. So in order for different reactions to happen that way, you also have to have things that are kind of like promoters. Y'all ever have a friend that just makes everything worse? They stir up the drama.
Yes. Yep. Oh, this community knows some drama. Like even in the time that you've kind of been away from everything, like, you know, there's always been stuff.
There's always been drama. I've had to deal with drama when I was, man, so much drama. People be like, this person made a hate video about you on your birthday. And I'm like, well, you know what? I was having a great time. I don't even care. It doesn't matter, you know? So whenever you get a reaction to happen between things like that in organic chemistry, you got to have somebody to stir up the drama. Sometimes it's a strong base. Sometimes it's a strong acid. Sometimes it's not an acidic, but what we call a polar solvent. It just doesn't have a hydrogen that can, it's an aprotic polar solvent. That's like the term, meaning, hey, this particular stuff that we can throw stuff into isn't going to act like an acid, but it's got that, shift of electrons more on one side than another. And we need that to get this reaction to go. So it's not enough that the two things are there. You also have to have a third thing to make the reaction go. Sometimes it's light. Sometimes it's, it just depends on what you're working with. So chlorine gas is so bad for you because once it hits light, it can break up into individual, what we call free radicals. Y'all hear that on like oil of Olay commercials. You need this to reduce the free radicals in your skin. Well, what it's talking about is chlorine having one electron, but it needs another one in order to be satisfied. So light can cause chlorine gas to split, which means that's why it's bad for you, because you breathe in it in its free radical form and it'll be like, but that's not a thing either, guys. The free radical stuff. Just eat some berries.
And you need free radicals in order for your body to function. Like the electron transport chain runs on free radicals. If you didn't have those, and specifically in this case, like free electrons, like you could not make ATP. Like you would have no proton gradient, none of that stuff. So it's important.
I mean, it's controlled free radical movement. Your body has things in place to help keep those certain things secure. Now, if you're getting into disease, where you have the absence of an enzyme or you have the absence of something and those things aren't contained, that's when you start getting into medical treatment. That's different, right? That's different.
Yeah. That's why they test for certain enzymes to see if you can eat fava beans, because fava beans can stir up a whole lot of free radical nonsense in people. So
so you've got, there was a guy who is a cardiologist who is the resident doctor for Goop. I say that because he's just terrible. He presented a paper at the Paris Institute. Not a peer-reviewed paper. It was a study that he did on like 8 people or something. And he noticed that if he gave them supplements, then their autoimmune disease was lessened. But he gave the supplements intravenously. And all of these people had gluten-based autoimmune issues or gut-related autoimmune issues. So yes, that is supplement treated usually. But if you don't have that type of autoimmune disease, getting supplements from Goop isn't going to do anything for you. And taking it by mouth versus IV, that's a completely different pathway.
100%.
It doesn't work that way. So you encounter a lot of people. Now, I'm in my 50s, y'all. I'm 51. And people are like, how you look so young? I'm like, sex, drugs, and rock and roll, baby. Yeah. It's probably genes, if I'm honest. But, I try to eat right. But I do have a dietitian because I'm prone to both ends of the eating disorder because I grew up in poverty. So poverty trauma contributes a lot to mental health issues. If you haven't dove down that rabbit hole, have a look at that. So it's like if it's buy one, get one free on coffees, I'm like, yes. And I'm like, I can't drink both of these, or I'll panic buy and fill my like kitchen with stuff. And I'll be like, wait a second, I can't eat all this. So it's like, anyway, I see a dietitian, and because I'm 51, because I'm perimenopausal, I tend to have deficiencies in certain things, and I need to take supplements because I'm not always eating the way I need to because I'm working on that. If you're being told by a medical health professional that you need to take certain things in order to feel better, in order to, limit, like reduce your inflammation. AI disease runs in my family, mostly rheumatoid. It's all inflammatory stuff. So I'm listening with a filter
Yeah.
from my dietitian who worked in a renal failure facility for like
Okay.
15 years. So she worked with patients who had, renal failure, and she would help them figure out what they could eat and things like that. So it's pretty
Mhm.
cool on that. Oh, I just got your message.
Oh no, you're good. That was a while back. Uh,
But, so you got to kind of, I always say, listen to your doctor. But if your doctor's telling you some things that sound weird, go to another one and ask them too.
yeah.
That's not gonna hurt you. Um,
This is why it's important to become scientifically literate. And it's
yeah,
not saying that you have to be an expert in all of these subjects, but to know enough of the basics to say, uh, does this make sense at all? Like uh, learning how to spot red flags of bullshit
right,
that people are going to try to sell you. So if we learn these things today about different functional groups and someone says, "Oh, well, uh I mean, I've never heard this, but if someone said amino acids are bad for you, you could say, "No, I know that that's not true because amino acids are just a molecule with certain functional groups on it, and you're not giving me enough information
right,
to make me believe you."
right.
So that's why we're here talking about all this stuff.
That's exactly right. So I find talking about how, I always use the sodium and the chlorine gas because those are things that people know. They know about that. You can even send them a video of people blowing up a toilet with sodium metal if you want. I show it in my general chemistry 1 class. I'm like, y'all want to see a toilet explode? And they're like, yes. And I'm like, of course, let's do this. I'm still trying to convince the dean to let me do it in the parking lot. Nobody was letting me blow up a toilet in the parking lot. I'm like, but it would be so cool. And they're like, no, no, no. I'm like, but it's for science. And, I just get
Oh,
stonewalled, like,
yeah,
nope.
and like we were talking a few weeks ago about peptide therapies, and there were very different definitions people were using for peptide therapy because to the common public, peptide just sounds like a fun scientific term, and they don't really investigate too hard. But uh, one MLM company was selling peptide supplements that was literally just fava bean powder and some vitamins because we know the peptides are just chains of amino acids that end up making proteins.
I mean,
And so it doesn't tell me anything when you just say these are peptides because the other companies that were selling peptide therapy were selling anabolic steroids.
oh my gosh. Um,
Essentially, like, they're selling, like, growth hormone analogs and, like, okay, yeah, these are all peptides, but this is where we need to understand the word peptide isn't talking about what it does, that's just what it's made of. That's just the
yeah,
building block. It tells us nothing about what the medication is, what the supplement is. So that was a big one from recently. It's just funny because like people buying it was like $150 for like a 30-day supply of this
gosh, man.
fava bean supplement. Like, just go eat some fava beans.
Just go
Unless you
eat some
have
fava
one
beans.
of those enzyme deficiencies we're talking about, then maybe don't. Maybe not for you. But
The term peptide comes from peptide bond, which means the bond between an amine and a carboxylic acid.
yep,
A polypeptide is a protein.
yep.
So you could, if you wanted to, you could like change out all of your language that you use in a day with the scientific terminology, and people will think that you are just so smart. You could be like, yeah, I've completed the amount of the hydrogen monoxide that I needed today. I do keep track of that because it's really important that I hit that goal. And the polypeptide amount, I needed to get about 30 grams of that. I need to make certain I start out with my morning with 20 grams of polypeptides. And I take that before I take my caffeine because I really want to get my metabolism a good solid, get it started going. And then I also want my circadian rhythms to sync up appropriately so I don't have insomnia. So I make certain that I get my photosensitive vitamin D by stepping out into the sunshine. So it's like,
Yeah,
all I said basically is, I drank a protein shake this morning.
yeah.
I drank all of the water that I was supposed to have, and I walked outside. So it's just, now give me $100. That's my plan for you.
So since we have the functional group thing pulled up,
Yes,
and we have the um I know I see the ether section up there. I know we have the alcohol section
right.
somewhere on that page. But with uh the concept of methanol versus ethanol, I know
Oh,
you and I
okay.
know
This right here.
this particular thing, but going into, you know, uh methanol isn't ethanol and
No,
methyl mercury isn't ethyl mercury. And
no.
so while if you have the same functional group but a different amount of carbons, or a different
Mhm.
location on the carbons, how does that change it? And how would you explain this concept to somebody who has no idea what we're talking about?
Okay, so if you drink methanol, you're going to go to the hospital. It's very, very bad for you. Your body can't really break it down. And the reason why it can't break it down is because it doesn't have as many carbons as ethanol does, right? So here's what we call ethanol versus methanol. Methanol has one carbon and it just has three hydrogens and it has that OH group. So this carbon is surrounded by hydrogens essentially, and it's attached to an oxygen. Now remember, this oxygen is pulling on all those electrons. So this is not an even sharing of electrons here. Carbon absolutely has to have four bonds or it's going to be unstable. It either has to have four single bonds, it has to have two double bonds, or it has to have a double bond and two single bonds, or it has to have a triple bond and a single bond. It has got to have that total set of 8 electrons in some form. Now, we look over here at ethanol. This is a carbon here where this point is. Now, here's a rule for you for organic chemistry. If you see these little line structures, they're called skeletal structures. The hydrogens are implied. So this one shows the hydrogens there because there's only one carbon. But this, every end and bend is a carbon. So this has a carbon here and it's got three hydrogens. This has a carbon here and it has two hydrogens on either side. But the difference between here and here is that carbon's got a nearby buddy. Okay. Carbon's got another carbon nearby that can lend it a little bit of support with electrons, as opposed to this one. Hydrogen doesn't care. Hydrogen doesn't really care about electrons so much. But if you've got a nearby carbon over here next to this carbon, you can break this molecule down a bit easier than you can methanol. Methanol is not going to break down as well as ethanol will. And besides, we have an enzyme to break down ethanol. We do not have an enzyme to break down methanol. So that's one of the huge differences. Even by going over here, you notice this one is what we call 2-propanol. So propanol has 1, 2, 3 carbons, and the OH group is attached to the second one. That 2 lets us know it's on the second carbon. So if you learn the jargon here, this 2-propanol tells me on the second carbon that OL means I have an alcohol group. Prop means there's 3 carbons. That AN means they're all single bonds. So this is a 3 carbon, all single bonded on the second one is an alcohol group. That's why a lot of organic chemistry 1 is nomenclature, just learning what the words mean. Then here we've got 2-methyl, 2-propanol, T-butanol. So I this is fine, this tertiary butanol. I teach my students this, the 2-methyl, 2-propanol, because you can't go wrong with numbers and labels. If you just remember this part, you're going to be fine. So I have 3 carbons. On the second carbon, I have a methyl group, which is that CH3. And also on the second carbon, I have an alcohol group. So this tells me everything I need to know. So since I have more carbons here, this one is going to behave differently than this one. This one's going to behave differently from this one. And then they're all going to behave differently than this methanol here. Just adding the additional carbons is going to change the functionality of each one of these molecules, because if you have more carbons, then it's easier to pull these functional groups off. If you have less carbons, it's a lot harder to do that. So methyl versus ethyl is really important. Methyl is 1 carbon, ethyl is 2 carbons, propyl is 3. So propane and propane accessories, if you're a King of the Hill fan, that's 3 carbons, all single bonds, all covered with hydrogens, right? So yes, but this is also important too.
Yeah, and so that's the same concept as methyl mercury versus ethyl mercury.
Yes.
Right.
They behave very differently, very differently. So how are we doing? Any questions in the chat?
I think all the questions are answered. I think there was a slight discussion in the side chat about the difference between organic chemistry and general chemistry, and I think they did arrive on the conclusion that organic chemistry is a subset of chemistry and not, it does not operate with different rules. It's just a specialization of chemistry to get more in depth on carbon-based reactions.
You've got cancer research, and then you've got epithelial, then you've got, kidney, then you got neuro, So you got chemistry, you've got organic, you've got inorganic, you've got physical, you've got analytical, you got theoretical, you got quantum, So yeah. You have all of the different lenses of chemistry. So yeah. One important thing that we really need to discuss when it comes to structure in vaccine technology is something called hydrogen bonding.
Oh, yes.
Hydrogen bonding is so important. This is why water is cool, So water is pretty cool because it has a high heat capacity. So when we sweat, all of the heat is absorbed by the water. So when a cool breeze comes by, we feel cooler because that water is absorbing the heat off of our body. So, flip side of that, Dr. Ben would know this. If you're in some place like New Orleans in July, I did this. I was and I'm prone to sweat because I'm 51 and perimenopausal. You know what I mean? I'm hot and cold at the same time. It's the weirdest thing. I don't care for it, but here we are. So I went to New Orleans in July. So hot, you're sweating, but you're right there at the Gulf, right? You're right there at the Gulf. So it's super humid. So the opposite problem with that is if you have all this humidity, all of this water is on you, it works then as an insulator. So it does absorb the heat, but if the water doesn't get blown away, you don't get cooler. So you just get hotter and hotter. So water has this because of hydrogen bonding. It's able, and this is where I use the term sexy oxygen. If you have an oxygen and a hydrogen on one molecule, you can have another molecule that has an oxygen and a hydrogen, and it's going to be attracted to the hydrogens on other molecules. So oxygen will be looking for a third party in the form of hydrogen on other molecules. Now, oxygen is not the only one that does this. You can also have it with chlorine, and you can also have it with nitrogen. But we tend to look at it more from the oxygen and hydrogen perspective, and also nitrogen and hydrogen, particularly in the helical structure of the DNA. That's what causes that spiral, that twisted spiral between those nucleic acids. You have hydrogen bonding, and their lowest energy conformation, their energetic favorability, is in that twisted form. It takes energy to untwist it. That's where we get the helicase and all of that to kind of deal with untwisting that DNA. But this is also important for turning on and turning off cellular receptors. One of the research things that I did when I was in grad school was studying the LPA2 receptor. The LPA2 receptor is highly expressed in epithelial cancers, particularly breast cancer. So if that receptor is on that cell and it's fired off, what happens is the cell undergoes cellular rescue. So what's supposed to happen is if you have a cell that's no longer doing its job, it's supposed to self-destruct. But that LPA2 receptor on the outside of it, you have a whole lot of those on a cancer cell. All you have to do is fire off one of those. That cell is going to protect itself and keep itself from self-destructing. So what I did with that particular project that I was working on is I used Mo software, which is molecular orbital environment. You can put a protein in there. You can put a receptor in there, particularly receptors, but you can put a protein in there, find what its natural shape is, its lowest energy conformation. And you can see how different compounds interact within that receptor. Now, what turns on a receptor and what turns off a receptor? Like 85 to 90% of the time, it's going to be hydrogen bonding. The more hydrogen bonds you have, the more response you're going to get from that receptor. So sometimes if you turn on a receptor, then that's going to initiate whatever thing that receptor is responsible for. In case of the LPA2 receptor, that's cellular rescue. Well, we went through and tested different antagonists. Those are compounds that will bond to the receptor, but it doesn't turn it on. If you plug up all of those receptors and you don't have it doing its function, you can prevent it from being effectively turned on, right? Does that make sense? So it's kind of like plugging up the key or plugging up the lock so the key doesn't fit, right? So you've plugged up the lock, but you're not doing anything with the doorknob. It's just plugged up. Nothing else can fit there. The door can't open. Well, vaccines work in a similar way because you got to look at how do viruses get in a cell. I guess I could pull up, let me stop sharing for a second. And I'm going to pull up some images here because this is really important. Hydrogen bonding is going to be like a big thing. We can look at the COVID vaccine or COVID virus. I'm going to pull that up really quick. Is it going to let me? Why is it not letting me type? Oh, there we go. Let's see, ACE receptor. Why is COVID so bad? ACE2 receptor. That's what it is. I talk about this in my class too. Let me find a very, very, very basic picture. Okay. Here. Let's see. Let's see if I can. Oh, that looks scary. Okay. This one's not so bad. All right. I try to actually find pictures that aren't terrifying for students. All righty. Let's see. This is going to...
Okay, I've shown the full, full metabolic pathways diagram on this show before.
Oh my goodness.
So just to make a point.
Okay.
For all the people that try to simplify metabolism to be something grifty. Like, no.
Let me see if I can zoom in a bit. I'm on my Mac and I've never thought about zooming in. I have like all of the little keys on here. Anyway, where is the one for zooming in? I can't find it. So this is the downside to having this.
Yeah.
All right. I don't know how to. I guess I could save it really quick. I don't know. If I save it and then pull it up. Oh, no, it's a WebP. Anyway, let me see. I'm going to let's find a better picture. Here we go. Let's see if this one's better. Okay. There we go. All right. Let's look at this one. This one's a bit better. It has other terms in here. But essentially, let's see. I need to reshare.
Yeah, if you share that one.
Okay. I'm sorry. I'm being silly. Okay, here we go. This one's better. Okay, this one's better.
There we go. Okay.
Okay, so this one's better. We can completely ignore these words if these words are freaking you out. We don't need to look at that at all. Here's an example of a COVID virus. You've got a COVID virus with all the little things, those little nubbins on the outside. Those are its receptors. And inside the virus, you have all of the stuff, the viral genetic code that hijacks your cells to make virus parts. Well, how it gets in is through those little nubbins on the outside. Those are all, if you can imagine, if that was a circle and all of those were keys that could fit into the door of your house, and your house are your cells, right? So you have a robber or a thief or whatever, maybe, I don't know, maybe a nosy neighbor. They just have all the keys to your house to just to one lock though. But that one lock happens to be on every single door of your house, which makes COVID particularly nasty because the ACE2 receptor is on just about in every cell of your body, right? It's I think there's very few exceptions where you don't find the ACE2 receptor because it's particularly important in cellular function. So what's happening here, what's going on between these little nubbins on the outside of this COVID and that ACE2 receptor that's on all of your cells is hydrogen bonding. So it comes along, it can fit right into that little lock, which is your cell receptor, and it can open it up. And then it enters and has all of its insides end up going into the cell, and it hijacks your cell, and it turns the house of your cell into, I don't know, we could say a meth lab if you want. It doesn't, they're making
Which
bad.
that is within the realm of organic chemistry, not one that we're teaching or advocating for, but
Yeah. Oh, I have to tell y'all a story about the campus police at my campus. They're so worried about students making meth in my lab. And I'm like, no, you need to worry about them making a bomb because that's way easier. But actually, it's my biggest concern, particularly with lab safety, is domestic abuse and domestic violence situations, because it's real easy just to grab a big old bottle of acid and take it home and hurt somebody. So yeah, so that's the biggest thing. Self-harm, domestic violence, make a bomb, meth is not even on that list because you require certain skills. And to be honest, you can get most of the stuff at Walgreens anyway.
Yeah, well, so you can make some positive things though too, like soap. Yeah. I'm making soap. And that is organic chemistry.
Soap is great.
Yeah.
In my organic chemistry class and for my lab, I do a lot of practical stuff. We make aspirin, we make soap. I show them how to separate caffeine from coffee, tea. We do all of that. So
I remember the aspirin lab. I think that one's a pretty common one to see in organic chemistry classes. I think we did that one too.
Yeah, I thought about it might be cool to set up distillation and make our own whiskey, but I don't know. Like, this is how to make whiskey, kids.
I remember it, and this is like not at all related to this, but I remember there was a time it was Orgo 1, which like Orgo 1 lab, for people who haven't done it, is a lot of learning the lab techniques and not really making a whole lot of stuff. You're learning how to do the things for organic 2. Yeah. And we're all like such anxious pre-med students, most of us. And so we're all like freaking out about trying to get an A on everything. But our lab instructor decided he was going to go off book, like off from the lab book, and change one of the solvents or something, because we were supposed to be doing a liquid extraction, and we all ended up with like 200% errors in our yields because he instead gave us something that was soluble in water, Like, this
Wow.
isn't going to work. That defeats the purpose of the extraction. So we
Yeah.
all freaked out, and I remember crying so much that day because I was like, how did I get this bad of a result? It was
Oh my
not me.
gosh.
It
Yeah.
was not
See,
me. It was because he changed it. I think he changed it from like vanillin to vanilla alcohol, which,
oh, those are
because
two
it
things.
smells better, it's like, no, you cannot extract the alcohol from the organic layer system.
No, that would be Frodo, my very angry boy. He
Oh,
hates everything
shoot.
except us. He's just, and he has like a Jim Henson face. He has like a Muppet face. He
So
looks
cute.
like Falcor from the Neverending Story, but he's a black dog. So I don't know. But yeah, you can't do that. You can't just be swapping stuff out thinking I like this instead. It smells the same. No, cyanide smells like almonds. Don't eat it.
Yep.
And cyanide, really interesting. Carbon is triple bonded to a nitrogen on cyanide. And carbon has a pair of electrons hanging out on the other side. And in that case, I believe the negative charge is on carbon. Carbon is a freak. It does not like to have a charge. It doesn't like to have unattached electrons. Carbon is not stable in that form. So cyanide is bad for you because that carbon's going to hook up with anything it can. And it does. So it's all about where the electrons are. And so if you can remember that, if that's the lesson you remember and go, okay, which one of these things has the electrons? That's where the action's going to happen. I try to teach that early on. A lot of my general chemistry students end up taking organic from me. So I'll see them for like 2 years. And I try to prep them to say, these are the things, if you're taking organic, these are the things that you're going to need to remember. So star this in your notes, write this down. This is going to be helpful. So I could talk about this stuff all day. Y'all are in trouble.
It's so good. No, it's such good stuff though. I think the chat's getting interested too. And yeah, for the people asking about how kidneys do filtering, y'all are just asking for me to do a whole kidney episode. Like, I will do it for you all. Like, you don't have to push or pressure too hard to get that to happen.
It's like a washing machine in the spin cycle, right? Those little nephrons spinning around and round and round. And then the water shoots out, and then you got the other stuff right in there.
Yeah.
That's pretty fun. Yeah, kidneys are important. So take care of them if you can. As far as like the hydrogen bonding, that's how you turn on, that's how you can turn on or turn off cells or just block the thing completely. So because COVID has all the keys to get into the cells, what we want to do is prevent it from doing that. So I'm going to stop sharing for a minute and we're going to pull up an image. I'm spelling stuff wrong. Come on. Get over there. I don't want to do AI ask mode. Y'all, I don't ever do that. Let me see if I can find a good picture. No, I don't want, see, AI never gives me what I'm actually, I don't want it in. They autocorrect on for in for on. All right, so here we go. Let me see if I can share this image. All right, let's see if we can go with this. Share screen. Here we go. All right.
Awesome.
Here we go. So this is a simpler drawing. So we have our human cell with our ACE2 receptors on the bottom. And then we've got our COVID, and it's got all of the keys that it can use to fit into those receptors. And it's able to have the appropriate amount of hydrogen bonding between those COVID receptors and your cell receptors to where it initiates an interaction between itself and your cell, to where your cell allows it to enter. Okay. So what antibodies do is they attach to those receptors on the COVID virus and basically put gum on the keys. So if COVID has the keys to enter your cell, we want to put gum on all of them. We want to keep that nosy neighbor out of your house. We want to keep the robbers out of your house. So if you put gum on everything, it's like a Home Alone situation, I guess, is what I'm thinking. All of your keys have gum, you losers, you filthy animals, or whatever
We
it is.
just need to make a parody of Home Alone, but it's about the COVID vaccine. It's about vaccines in general, putting gum on the keys.
Yeah, we do. So this prevents that hydrogen bonding from happening between the the COVID viruses and your cells. Now, notice we still have keys available here on this COVID virus. We have some antibodies attaching to it, but if you have enough antibodies, it's going to cover a lot of those and prevent those viruses from actually attaching to your cell. So the goal isn't necessarily to cover all of them, it's to cover enough of them to where they cannot effectively attach to your cell. Now, the ways we get the antibodies, well, we can get sick and our body will make antibodies, or we can introduce the proteins that are associated with the COVID to where your body will recognize the proteins and make antibodies. But here's the thing that anti-vaxxers don't quite understand. The proteins that generate the immune response are not the same as the virus. It's like all we're doing is taking those nubbins and introducing those keys to the body, going, hey, here's a random protein that you don't recognize. You maybe ought to do something about it. And then it does. It makes the gum that fits on those little random keys. So the other thing, so we've got one where you can introduce a deactivated form of the virus where it's just the proteins, or we can do the messenger RNA situation. And that's where people get really freaked out. They don't understand that this technology has been around since probably the late 80s, early 90s kind of thing. It's been around for a while. It just hasn't had a lot of funding to push forward. And that's the thing that people don't understand. We can only do as much science as we have the money for, right? Used to, we would have a lot of funding. If we look back in the 60s and the 70s, prior to the Reagan years, science was heavily pushed. It was heavily pushed. We put people on the moon. We got HeLa cells. If you haven't learned about Henrietta Lacks, you should dig into that. Johns Hopkins had a lot of funding, particularly with trying to sort out cancer treatments. Danny Thomas, who founded St. Jude, he was a TV actor and he made a deal with God, is what he says, to where if he became famous, he would open up a hospital. So at least he made good on his end, whatever you think. Whatever you think of that, we ended up having one of the most premier world-renowned cancer facilities. They don't just do cancer stuff. They also do vaccines. They make vaccines and they try to predict, like with the flu. Oh, hey, it's been a minute, hasn't it? Oh, what a decade
it's been a while.
This year has been.
No, but you say that they're not funding the science, but hold on, but they're doing the studies to make the proof that Tylenol causes autism, right?
I know. So when I went to grad school, one of the things that I wanted to do is I wanted to get into cancer research because I figured I'd always have a job. I'm like, because everybody, I hate to use this term, but cancer is sexy. Breast cancer is sexy. Erectile dysfunction is sexy. That's all the stuff that people want, for that. That's what we're constantly bombarded with. Like, we need this and we need that. They're like, well, we don't need to study this rare disease over here because a lot of people don't have it. So who cares? So a lot of it has to do with marketing, and a lot of it has to do with public opinion on what gets studied. So we don't see a lot of different things. So the messenger RNA, it was out of sheer desperation to try to stop this virus, because it's not like the flu. It can cause organ failure, and it does. It can cause, it depends on what your initial viral load is and how many antibodies you already had. So the thing about being infected versus triggering an immune response from a vaccine is that being infected, you run the risk of death, right? You run the risk of organ failure. You run the risk of all of the things that can happen. And this is where, so I have a nephew, and he was years ago diagnosed with Ewing's sarcoma, which is a bone cancer, and he lost his leg, but he's alive now, and he's been clear for about 5 years. So we're super happy about that. Something that I had to remember, because I've done cancer research, I can read studies, I can panic about it forever, is that there is no statistical patient. I mean, there is no such thing as a normal patient. Every single patient is going to have the potential of different outcomes depending on what their variables are. And that's something I had to remember, because I'm like, oh my God, so many kids die from this and blah, 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 and all of that. And he has lesions on 3 parts of his body. This is awful. And then my science friends, like Doc Savage, would be like, because he's been in cancer research, he's like, okay, Mel, you're not an oncologist. And I'm like, you're right. He is in the best hands he could possibly be in. These people, they are in a research, and he went to St. Jude and they saved his life, but this administration cut funding to St. Jude, and it makes me insane. It's like, so you just don't want to save kids or prevent death. Fantastic. So it's just funding.
Yeah.
Funding is a huge drive on what gets what. So when the messenger RNA thing was coming up, people were like, this is new. Well, they just hadn't heard it before. It's been around for a while. We didn't throw everything into it until we needed to. So all this messenger RNA stuff is, RNA falls apart within 8 to 12 hours, depending, on your body. It completely falls apart. So what happens is your cells will uptake the messenger RNA. The ribosomes will read that genetic code in there, but it's not DNA, it's RNA. And it's not being put back into your nucleus. It literally falls apart within the cell into its individual nucleotides. So you've got guanine, cytosine, adenine, and uracil. DNA doesn't have uracil, it has thymine. Okay. And in order to get genetic code into the nucleus, you have to have a type of protein that can carry it into the nucleus. Even if you had DNA injected into your cells, there's no guarantee that it's going to be carried back into your nucleus. HIV, which is a retrovirus, has the proteins that can carry that genetic code and put it into the nucleus. That's a different thing. But, so the messenger RNA vaccine, what it does, it convinces the cell to make the proteins as if it was hijacking it, but it doesn't actually hijack it. It just reads the stuff, makes the proteins, and that's it. It falls apart after that. So your body makes the viral proteins, but it doesn't change your genetic code because it can't. There's nothing there to put it back into the nucleus. See, that's one of those things. It's just because you have the presence of the thing doesn't mean it's going to happen. So I mentioned before with the organic chemistry and the reactions, you have to have a shit stirrer. You have to have a promoter. You have to have something that causes the reaction to happen. That has to be present too. It's not enough that it's just there. You have to have something that causes the reaction to happen. Much like if I take all of the ingredients to make a cake and I mix it in a bowl and I set it on my table and I go, cake. It's not
Not
going to
really.
do it. I have to have the introduction of heat in that case to get all of those things to mix together and react with each other. That's a very basic fundamental thing. So if you encounter anti-vaxxers, they're like, well, it has genetic code in it. You're like, yeah, but it's messenger RNA and it falls apart right after it's read by the ribosomes. And two, there's nothing to carry it back into the nucleus and get it to turn into DNA. There's nothing there to do that. You have to have something carry it into the nucleus. It just doesn't go there by itself. And then you can use the cake analogy. Well, you have all of the ingredients there. Let's just say you don't even mix it together. You got all the ingredients there and you put them in the bowl. Cake. It's not the same. You got to stir it up. You got to add all this extra energy to it to get it to turn into cake. It's the same thing with that messenger RNA, but people don't
Yeah.
think that.
And it's a misunderstanding of what role messenger RNA has even in the transcription translation process.
Yeah.
Like its role isn't to modify the DNA or replicate DNA, it's to make proteins. Like
Yes.
that's the whole thing. It's down the chain farther from what the DNA is actually doing. It just says this is the protein that needs to be synthesized. So it's not even involved in that DNA modification process. Like you don't have like the whole HIV example, like Mel was saying, there are specific enzymes that are required
Yes.
to make the RNA impact the DNA at all. And that's kind of where HIV treatment targets those mechanisms. But your body doesn't really contain the ability to do that on its own. We're not retroviruses.
Right. So HIV has an enzyme that can turn RNA into DNA. And then it has a separate protein that can carry it to the nucleus. So it has two things there. It can convert RNA into DNA by swapping out that, by going back and doing a transcription. It's reverse transcriptase is the name of that enzyme. So it'll go through and do the reverse. And then it takes that code, has a separate protein, and carries it back to the nucleus. Those are two additional things two steps that are completely missing with messenger RNA. Messenger RNA at best is a recipe that is like a text message or like a Snapchat that just vanishes after you've read it. It's like a message that just goes away. If you're like me and you're like, I know I have this text message somewhere. Where did it freaking go? So it's just like a sea of text from somebody. I got to find this text message.
Yeah. It's like someone standing outside of your house with a recipe for a cake on their phone and you getting mad that, oh, well, doesn't that mean you're just going to walk into my house and start making a cake in my kitchen? No, not at all.
Not at all. And so when we're introducing the recipe for these external viral proteins that your body would experience if you actually were infected, your body would experience these viral proteins anyway. That's why some people feel like, oh, I'm a little sick, because the response that you're getting from your immune system is exactly what would happen. Not exactly. It's a small difference than what would happen if you actually got the virus. So your body has an immune response. It's rushing to those cells that have that messenger RNA and making those proteins. And it's going, hold on, what's going on here? And then it goes, we're being invaded. So it rushes to where the infection is. And it starts making antibodies to block up those proteins. So all you're really going through with messenger RNA based vaccine versus a deactivated virus is your cells are uptaking that coding, making the viral proteins as if you were infected, but you're not. And then you've got antibodies that are made from the expulsion of those proteins from the cells. And yeah, you might feel a little sick because you're getting an immune response to that. You might be like, oh, I felt kind of gross after a vaccine. Well, I've had COVID and my immune response was so strong. I had already been vaccinated. I got the boosters. I was teaching a class and one of my students came to class sick and told me that they were sick. And there's like, but I'm wearing a mask. I'm like, I don't care. Don't bring that here. Don't bring that here. I'm like, my nephew is on chemotherapy. And at the time, I wasn't actively going to visit him because I didn't want to make him sick. I'm like, don't bring that here. It's so selfish of people to be sick with that and come to class. I got COVID. I could feel myself slowly decline. I had to go to the emergency room twice. First time they did a PCR test, couldn't detect it. But I had all the symptoms and all the signs because my body was fighting it off so hard. It didn't register as a positive test because I didn't have much, but I felt like shit. I felt awful. Yeah. And then the next day, I went to my general practitioner and they ran one of the flow tests, and there was a very light positive. So the thing is, if you want to feel your immune response, that was a very strong immune response that probably would have killed me had I not had those antibodies. I don't know what kind of viral load I breathed in, but I had antibodies to start with, and I have allergies and I'm prone to autoimmune disease. So I have a hyperactive immune system as it is. But that's the thing that was killing people in the hospital, was that strong initial immune response, that cytokine storms, as they call them. So it's like, so do you want a vaccine that's going to make you feel a little sick from an immune response? Or do you want to get the actual virus that's going to make you feel like you're dying and your immune system might actually kill you? So it's kind of like, ugh.
And with no guarantee that you're actually going to develop immunity. Like since the vaccine has a consistent dosage and a consistent response that you can expect from that, the risk is very minimal for getting the vaccine compared to the benefit that you're going to get. However, from getting the natural infection, sure, you may get immunity, but you may not. And the risk that you're taking is way, way higher for a less guaranteed. And that's, and I mean, you're not guaranteed anything from a vaccine either, but it's a higher likelihood, much higher likelihood that you're going to be able to get some immunity from a vaccine compared to a natural infection. So is it worth all of that to maybe not get immunity? For most people, no.
Yeah.
No, I mean, it's not worth it.
It's not worth it. And I swear to God, I actually made little short films I sent out to my students, like sharing is caring, except with diseases. Don't bring me your diseases. I swear to God, I will get so mad at you. I got so angry at the student who gave me COVID. I went off on my class about it. And some of my students got really upset. She blamed us for getting COVID only because my student told me that they had it. I wouldn't have known otherwise. They just thought it'd be okay just to come to class anyway. I'm like, no, stay home. I will give you more time if you need it, because I'm not a jerk. Don't come to class sick. Man, what's wrong with you? So the antibody response that you get, like Dr. Ben said, from the vaccine, we have the data to show that it's a much higher response from the vaccine than being infected. And it reduces your risk of death. It doesn't reduce your risk of being sick. Clearly not. I got COVID, even though I was vaccinated, but it didn't kill me. It made me feel awful, but I'm not a statistical patient. So it made me feel awful, but I didn't die. I didn't die. Other people die. So, yep. But
so
go ahead. Sorry.
While we're getting close to the end of the show here, I do want to ask, since we have this model up on the screen showing some nice antibodies and receptors, it reminded me of everyone's favorite topic within organic chemistry, sterics. Do you have any thoughts on sterics and how that impacts the chemistry and the kind of the myths in society? Like, are there any myths that you've heard that maybe a discussion on sterics would kind of help with.
Yeah, I can share my screen back to my summary sheet. Yeah, we didn't talk about that. We got real heavy into functional groups and really excited.
Yep.
But we
We
have
can always do some other parts too, getting into more acid base and
yeah.
stuff too later
So
on.
let me see. Let me see if I can find stereochemistry. Here, let me zoom out. So I just want you to know, I got all of these off of masterorganicchemistry.com. He does have, these are behind a paywall, but
if you're taking the class,
yeah, if you're
these
taking
look
my
very
class,
helpful.
or if you're taking a class, it's really, really helpful. You even have free radicals here, acids and bases. Okay, here we go. This is really important. Stereochemistry. So a lot of people don't understand that the shape of the molecule and how it is put together plays a role in how it functions within the body. So let me go to over. You can even get into plane of symmetry. I mean, that's a whole thing. And people are like, trans is just a made up word. No, it's in organic chemistry. It means on opposite sides of a double bond. Cis means on the same side. It's an actual scientific term. So if somebody's like, trans is just made up, show them a organic chemistry book and say, no, it's not. It's been around for a very long time.
Yep.
Stop being silly. So,
yeah.
Okay. So let me see if I can get some examples over here. Oh, I thought they would have examples here. Okay. Well, let's go into how we determine one thing versus another. All right. Here's just some basic terminology. RS convention. This is how we determine whether or not a molecule is R or S. Let's say that these numbers here are different functional groups. If you notice here, I've got, let's say this is like a really important functional group is number 1, then the second most important, then the third most important, then the fourth. And yes, we denote importance based on how big the functional group is as far as its atomic number. So the bigger the functional group, the higher, the more important it is. We'll just say that. It's a bit more nuanced than that, but for the sake of time. So here I got the most important one on the top. I got my third most important in the front and my seconds on the side. Well, here I've got my most important group going in the front, third most important is on the top. I mean, and how you're counting, whichever direction you're going when you're counting, that's how you determine if it's R or S. But these had, let's just say that these two molecules have the exact same functional groups, but they're arranged differently, which means they're going to behave differently in the body. So we've also got trans versus cis. Okay. So here we go. We've got R versus S. We got trans versus cis. So here, this alcohol group is facing out. Here, this alcohol group is facing in the back. These are going to behave differently because of the direction that they're facing. So how they fit into a particular receptor, it's going to be different. It's going to be different. Their hydrogen bonding that they have, it's going to behave differently because of how they fit in that receptor. Let's look at trans versus cis. So a trans molecule kind of goes like this. You got your groups on your opposite sides of your double bond. Cis, they're both on the same. This completely changes the shape of the molecule. So will it even fit in a receptor or not? And then if you got an alcohol group facing one direction versus one facing another, now, mind you, these are the exact same chemical formulas made up of the exact same atoms, but because they're shaped differently, they're going to fit differently in a molecule. Here's another example. We got carbons in a ring. We got one alcohol group facing in the back. That's what that dash means. We got one alcohol group facing in the front. That's what that wedge means. If they're facing different directions, it's trans. If they're facing the same side, it's cis. this is going to fit differently in a receptor. So when you're looking at these examples, S-pentanol versus R-pentanol, that one little change, that one switch of those groups completely changes the function of the molecule. There were some examples. I'm going to show you some examples here, and I might have to use AI real fast. Let me see. So I can get.
Sorry, I was muted. While you're doing that, I'm going to pull up the super chat. We got $10 from Miranda Rensberger. Thank you so much. Says, my sister, a CRNA in San Francisco, sometimes has patients request organic medications only. She enjoys telling them that all the drugs she gives are organic compounds. And they're always satisfied by that.
Okay. All right. So I did go through and I double checked this to make certain it was accurate. So just for the sake of brevity, I will use AI for this quickly from Google. And you can find this, the pharmacokinetics, and here's stereoisomers and drug toxicity. So I've checked, that goes into a bit more detail, but here's some examples. So thalidomide, thalidomide versus S, R has a sedative effect, where S will likely cause you to go blind. S naproxen versus R naproxen. So we have poisonous or inactive stereo isomers. So the fancy word for I've put it together in different ways is stereoisomer, because stereo, we think left and right. It's kind of the same concept. So are they coming out this way, or are the functional groups going back this way? So we use stereo in the sense of 3D, right? So we've got S-naproxen, pain relief, R-naproxen, doesn't do anything, and it's more toxic to the liver, so it'll mess you up more. DNL is another way. It's similar to the RNS configuration. It's just which sides are the groups on. So with penicillamine, D treats arthritis. It reduces the toxicity of metals. L version is toxic and it inhibits your vitamin B. D versus L. I mean, just rearranging those functional groups just a little bit can go from something that from medicine to something that's poison or not effective at all.
Isn't like a difference between like L-methamphetamine and D-methamphetamine, like isn't one more like able to be like a decongestant or something, and then like the other one is,
I think so. Let's
and
look
then
it
the
up.
other one is methamphetamine. I don't remember. This is
okay.
Sparking memories from when I took organic chemistry. Like, oh, all right, what's this example?
Let's see, phetamine versus D and methamphetamine. I'm probably spelling this wrong because I'm in a hurry. All right. Yep. So feature, primary effect, central nervous system stimulant. D-methamphetamine is a dextro. L-methamphetamine is levo. Minimal CNS activity, primarily a peripheral vasoconstrictor. So, so that isn't nearly as powerful as this. Low abuse does not produce a significant high for L-methamphetamine. This one, high potential for abuse because it has a euphoric high. This is in some decongestant inhalers. Man, if I didn't have like my freaking nose stuff to get rid of my sinus issues, I like breathing.
Some L-meth.
Yeah, so it's like you have the differences here just by changing that little shape, just from swapping out this one over here and that. I mean, it's just that simple, swapping it. So when you encounter anti-vaxxers that are like, oh, I looked up, this has methamphetamine in it. Is it D or L?
Yeah.
Which one is it?
Yeah, and of course, like you're gonna have in most reactions, depending on how much of a purification you do at the end stage. I mean, you're gonna have both stereoisomers present for the most part,
Right.
correct? But it's just the amount of it is going to be higher or lower depending on how you did the reaction,
Right.
correct?
So yeah, so there's here we'll go back to our stereochemistry screen. There's some misconceptions here. So it's not just so you're talking about a racemic mixture. So a racemic
Yes.
mixture is an example of I've done this reaction. Half of it is the stuff that I don't want, and half of it is the stuff that I do want. Well, some reactions do end up having that, but it depends on the type of reaction that you did in order to get your product. There are ways to do reactions without getting that racemic mixture. It depends. So, like, is it a substitution reaction? Well, okay, is it SN1 or SN2? Substitution, nucleophilic, bimolecular, or unimolecular? Is it an elimination reaction, unimolecular or bimolecular? Are we doing addition reactions? So, if you're trying to make a particular molecule, that's where the organic chemist starts to tap into that brilliance. They've got to come up with a plan to where they can reduce the chance of having the stuff that they don't want. And it's where they have to track, okay, I need to do this reaction first, then this gives me this. I can pair this up with this thing over here, and then I can do this reaction. Then this gives me this. So it's usually in order to reduce that racemic chance, you have to have a multi-step type of series of reactions so you have the best outcome. So
Yeah. And then thinking about their I know certain medications you end up wanting to use a racemic mixture, like with epinephrine versus racemic epinephrine do have separate clinical uses.
right.
So it's just interesting how like small changes or seemingly small changes to the stereochemistry can impact how useful something is or how problematic something is.
Exactly. And that's, this is where I talk about the importance of conservation. A lot of our medications that we've gotten come from the rainforest. And we'll see one particular plant, and it's like, okay, this is poison. But we find a cousin or a sister species that has the same plant, but it's a stereoisomer. Well, it's not the same plant, it's the same species, but it has the same molecule, same compound, same everything, but it's changed. Now all of a sudden we have medicine. And a lot of the reason why we have a lot of these medications is because we learned about this isomerism. That's a word for you. Isomerism. Isomer, and then the isms has to do with the process of where you got like the things are put together a bit differently. So we've like periwinkle, we found that in the rainforest. We've got a lot of different medications that we found for cancer. That one particular species of a plant, it was poison, and the other one was medicinal. So we see this in nature. It's not just something that we're sitting around cooking up in a lab. We start out finding these things in the wild, and then we go, oh, this is the molecule. Okay, now then we make the medicine within the lab, because we don't need to be mowing down all this land to grow the plants to make aspirin. You know what I mean? There's no need for that.
Yeah.
So conservation's important. So yeah. So for the people who are all natural, you need to also tell them, well, you do know why it's made in a lab, right? Because it's grossly unethical to like mow down indigenous areas and just start like the palm oil industry. Don't even get me started on that.
Yeah.
But it's like, that's grossly unethical. We can't just be doing that. We can synthesize these just like we find them out in the wild. Do you want to contribute to the extinction of all of the birds that would, there's so many birds we've killed.
For sure.
So yeah. So throw that at them.
All right. So I know we've gone for like an hour and 45 minutes ish. But have any closing things you want to kind of leave off with?
So I'm hoping I can get back into science communication. The current job that I have has taken so much of my time. And I'm actively doing a lot of work. I'm in a really high needs, low scientific literacy place. And I'm building lasting programs and changing lives. So it's like really important work to me. Because I know there are not that many professors like me that will work with students and help them understand the material. But I'm hoping to come back at some point. I am rebuilding my website. It won't be .com anymore. It'll be .org because I lost the .com. Somebody picked it up and was like, "You can buy it back."
No.
I know. So I let it expire. It was constantly crashing anyway. So I'm going to switch to .org. And I'll start building that soon. So if you want to go to scientistmel.org, if there's things that you'd like information for, I'll be blogging a lot on there. I'll reopen my store where we donate proceeds to, it's for my haters, the people that are really ugly to me. I put what they say on t-shirts and I donate to charities that they hate.
That's actually that's a really good idea. That's hilarious. I love it.
So organizations like Planned Parenthood, the Satanic Temple. I have neighbors that are like Trump supporters and they're super heavy Christian. They'll call like my local ordinance about her grass is a little too high. And I'll be like, well, you just got $66 donated to the Satanic Temple in your name. And they'll mail them a card and everything. It's great.
That's great. I might steal that a little bit and take some maybe one of the worst comments and donate to the Trevor Project with it.
Yes, the Trevor Project is another one that we would donate to. So whatever organization that would absolutely infuriate a hater, they're the ones that got the money. So I figured if I'm going to be petty, I can be petty. I'll respond this way. So every time they say something ugly, throw it on the t-shirt, donate the proceeds to charities.
That's awesome. That's so cool.
Scientistmel.org. Be looking for that. I'm going to rebuild it and I'll have materials there that you can share with others. I had a lot of teacher stuff there for a while too. So, and I am on Blue Sky. You can find me on Blue Sky. I'm not on Twitter so much anymore. It is just awful. Plus mine got tagged as like a freaking adult account. So you can't access my Twitter because somebody was like, oh, she's an adult star. And I'm like, no.
Is it because of the cam girl for science thing?
I suppose. Somebody said I'm a cam girl. So I was like, yeah, I am for science. Maybe. I was like overly, I used to have a lot of trolls just like report me for stupid crap. And so after a while, so I'm on Blue Sky. I have a decent following on Blue Sky and I post pretty regularly there. So you can find me there. I am on Threads, but not so much. But Blue Sky is pretty good. They have a lot of good scientists out there on that. So check that out.
Awesome. Definitely please do. Scientist Mel is great. And like I said, has been in this community longer than I have. It's pretty incredible. Also, Mel was one of the people there for Stool's penal prison thing. That was a time. But that's kind of off topic. But Scientist Mel is amazing. And I was super excited that she said yes to coming on this show. And maybe we'll have some more content in the future too. We'll see what myths RFK Jr. starts spouting soon, and maybe if there's something organic chemistry related, we'll go tackle that one. So.
Yes, and you can still see all of my old videos on my YouTube channel. I did lose monetization because I'm just not posting on it, and that's okay. I don't really do this for the money anyway. So, but you can see them, all the old videos there if you'd like. Oh, I haven't seen any of her stuff. I went to NASA at one point in time and I have the whole experience. I live streamed the whole time while I was at NASA, which was pretty great if you're a NASA nerd. So you can check that out.
Mel's YouTube link is in the side chat. So definitely click on that. I'm gonna pin it
Okay,
real
cool.
quick just so that we have it. Anything else? Anything else the audience should know?
I don't think so. I do, just so y'all know, on a personal note, I live really close to Memphis, Tennessee, and right now they're under federal occupation. And it's not making national news. A lot of people they've brought in state troopers, FBI, things like that, and they've torn up a lot of the old neighborhoods that I used to live in, looking for brown and black people. I know this isn't quite related, but I do a lot of activist work with Indivisible Memphis, and they have an immigrant pantry where they take food donations, and they also provide different immigrant services to try to keep people from being harmed. So if you're interested in that, I do have that information on my Blue Sky. If you want to help donate, they take their kids to school. They take immigrant kids to school because they're literally pulling parents out of cars and in the pickup line. But this isn't making national news. And we have people literally dying in our jail at 201 Poplar because it's so overcrowded. They're arresting people for traffic violations and not giving them bail hearings right away or letting them sign a bond release. So we have people dying in prison, and it's not making the news at all. So just stay loud, and if you can help at least get the word out, that would be great. I talk about that a lot on my Blue Sky. I'm sorry, did I make it really weird?
No. This is important to talk about, and I know my audience really wants to get involved and
Yeah,
help spread awareness on that stuff, and hopefully also help contribute,
yeah,
because
just
that is a
raising
huge
awareness.
deal that's going on. So I appreciate you bringing that up and sharing.
Oh, no problem. It's, it's part of Indivisible. I work with Indivisible Memphis, and I do try to be a resource, particularly for my immigrant students, because I have quite a few of those, and they're all scared. They're really scared.
Yeah.
So, if you want to learn more about that, you can find me on Blue Sky, and you know, help out if you can, or raise awareness.
Mhm.
Just stay loud. Okay. This
Yeah,
was fun, Dr. Ben. Thanks for having
that's
me
good.
on.
Yeah, and Ollie wants you to come play Star Wars on Sundays. If you happen to be around, let us know. Uh,
Oh, okay. Star Wars. What are we playing? Am I
uh,
gonna be
Star
Chewbacca?
Wars, Star Wars: The Old Republic. So it's a MMORPG. We can talk offline about that if you
Okay.
want.
Okay.
I'll let you know. We play on Sundays, so if you're around tomorrow, we'll be live here. And if you want to stop in and say hi, let us know.
Okay.
Thank you so much for joining us. Thank you everyone in chat. Definitely don't forget to like this video, subscribe to this channel and Mel's channel. Leave all your engagement, and we'll see you all next week. Bye everyone.
Bye.